Ethers and epoxides. Introduction. Organic compounds having COC as the functional group are called ether. The general formula is R dash, where R and R dash may be same or different alkyl or aryl groups, or one of them may be an alkyl group and the other aryl group. The divalent oxygen is also called the ethereal oxygen. Ethers in which the groups R and R dash are the same are called simple or symmetrical ethers, while those in which groups R and R dash are different are called mixed or unsymmetrical ethers. For example, diethyl ether, diphenyl ether, ethyl methyl ether, methyl phenyl ether. Ethers may be regarded as a functional isomer of the alcohol. For example, both dimethyl ether and ethyl alcohol have the same molecular formula C2H6O but different functional groups. Classification. Ethers may be broadly classified into the following three categories: aliphatic ethers, in which R and R dash may be saturated or unsaturated groups derived from aliphatic hydrocarbon. For example, ethyl methyl ether, methyl vinyl ether, divinyl ether. Aromatic ethers, in which either one or both R and R dash are aryl groups. For example, methyl phenyl ether, ethyl phenyl ether, diphenyl ether. Aromatic ethers are further subdivided into phenolic ethers and diaryl ethers. Ethers in which one of the groups is aryl while the other is alkyl are called phenolic ethers or alkyl aryl ethers. On the other hand, ethers in which both the groups are aryl are called diaryl ethers. For example, C6H5OCH3 methylphenyl ether, C6H5OC6H5 diphenyl ether, diaryl ether. Cyclic ethers. Ethers in which the oxygen is present in the ring are called cyclic ethers. They are further classified as simple cyclic ethers or crown ethers. Simple cyclic ethers containing one or two or three oxygen atoms in the ring are called simple cyclic ethers. For example, oxirene, oxetine, tetrahydrofurane (THF), tetrahydropyrene, 1,4-dioxane, 1,3,5-trioxane. Crown ethers. Cyclic ethers containing at least 4 oxygen atoms are called crown ethers because their three-dimensional shape resembles the shape of a crown. They are usually named as X crown Y, where X is the total number of atoms in the ring and Y is the number of oxygen atoms. For example, 12 crown 4, 15 crown 5, 18 crown 6. Open chain or acyclic ethers. Common system. The common name of the ethers are derived from the naming the two alkyl or aryl groups linked to the oxygen atom in alphabetical order and adding the word ether. In case of symmetrical ether, the prefix di is used before the name of the alkyl or aryl group. Some aromatic ethers, however, have their special names. For example, methylphenyl ether is called anisole and ethyl phenyl ether is called phenetol. IUPAC name. In the IUPAC system, ethers are named as alkoxyalkanes. The ethereal oxygen is taken with a smaller alkyl group and forms a part of alkoxy group, while the larger alkyl group is considered to be a part of alkane. The common and IUPAC name of some ethers are given in the table. CH3O CH3 dimethyl ether or methyl ether methoxymethane, CH3O CH2 CH3 ethyl methyl ether methoxyethane, CH3 CH2O CH2 CH3 diethyl ether or ethyl ether or ethoxyethane, isopropyl methyl ether or 2-methoxypropane, diisopropyl ether 2-propoxy 2-propane, methyl phenyl ether or anisole methoxybenzene, ethyl phenyl ether or phenetol ethoxybenzene, diphenyl ether phenoxybenzene. For further illustration, the IUPAC names of some other cyclic ethers are given below: 2-methoxyethanol, 2-chloroethoxyethane, bromoethoxybenzene, 2-methoxy 2-methylpropane, 3-methyl 1-butoxybenzene. Acyclic polyethers. Long-chain polyethers are named as oxide derivatives of the alkane corresponding to the total number of carbon and oxygen atoms present in the chain. For example, 2,5-dioxyhexane, 2,5-A-trioxynanon. Cyclic ethers. Common names. In the common system, the three-membered ring ethers are named as oxides of the alkaline from which they are derived. For example, ethylene oxide or epoxide, propylene oxide or isobutylene oxide. The names of the some cyclic ethers are based upon the names of their fully hydrogenated products. For example, furane plus 2H2 tetrahydrofurane, 4H pyrene, 2H pyrene, tetrahydropyrene, THP. IUPAC names of the cyclic ether CH2O and where and 2, 3, 4, 5 and 6 are given: oxirane, oxetane, oxolene, oxene, oxipene. The italicized portions of these names and suffixes are used to represent the size of saturated heterocyclic rings other than with n atoms. In case of substituted cyclic ether, the substituents are indicated by numerical prefixes with the oxygen atom getting number 1. Oxaminame cyclic ethers are also named as oxide derivatives of their corresponding cycloalkanes: oxycyclopropylene, oxycyclobutane, oxycyclopentane, oxycyclohexane, 1,4-dioxycyclohexane. Methods of formation from alkyl halides. Williamson synthesis. This is one of the best methods for the preparation of ether. It involves the treatment of the alkyl halide with the sodium alkoxide. The sodium alkoxide needed for the purpose is the by the action of sodium on a suitable alcohol. The reaction, in fact, involves the nucleophilic displacement of the halide ion from the alkyl halide by the alkoxide ion by SN2 mechanism. Thus, this method can be used for the preparation of both symmetrical ethers. For example, sodium methoxide plus ethyl bromide at 330 Kelvin, substitution reaction diethyl ether plus NaBr. Similarly, alkyl aryl ethers, phenolic ethers can be easily prepared by treating sodium phenoxide with alkyl halide. For example, sodium phenoxide plus methyl bromide on heating gives NaSO plus NaBr. Like halide ion, sulfate ion is a good leaving group. Therefore, in Williamson synthesis, alkyl halides may be replaced by alkyl sulfates. Sodium methoxide plus dimethyl sulfate gives ethyl methyl ether. Sodium phenoxide diethyl sulfate gives phenetol. Limitation: proper choice of alkyl halide and sodium alkoxide to be used in Williamson synthesis is necessary to the view of following consideration. Since a halogen attached to the double bond or an aromatic ring cannot be readily displaced by nucleophilic reagent, therefore aryl halides are not generally used in Williamson synthesis. Therefore, for the synthesis of simple alkyl aryl ether, the reaction is carried out between an alkyl halide and sodium phenoxide, and not between aryl halide and sodium alkoxide. Sodium phenoxide plus ethyl hydride on heat gives phenetol. Bromobenzene plus sodium methoxide on heating gives no reaction. However, if the halogen is activated by the presence of electron withdrawing group at ortho and para position, the halogen and such activated aryl halides can be used in Williamson synthesis. For example, p-nitrobromobenzene plus sodium methoxide gives p-nitroanisole plus NaBl. We have stated above that Williamson synthesis involves nucleophilic attack of the alkoxide phenoxide ion on an alkyl halide. Now, depending upon the structure, alkyl halide may undergo substitution or elimination reaction. Therefore, for the success of this reaction, it is essential that the alkyl halide used must be such which predominantly undergoes nucleophilic substitution. Since primary alkyl halides are more susceptible to SN2 reaction, therefore the best yields of unsymmetrical ethers are obtained when alkyl halides are primary and alkoxides are maybe primary, secondary, or tertiary. For example, tert butyl ethyl ether is prepared by treating ethyl bromide with the solution sodium tert butoxide. Sodium butoxide plus ethyl bromide gives butyl ethyl. The above ether cannot be prepared by treating sodium methoxide with butyl chloride or bromide. Since under these conditions, alkene isobutylene is the main product with the secondary alkyl halides. Both substitution and elimination occur through giving a mixture of ethers and alkenes, but with tertiary alkyl halides only elimination occurs giving alkenes. Thus, when a mixture of butyl bromide is treated with sodium methoxide, butyl ether is not formed, but instead 2-methylpropene isobutylene is formed due to elimination reaction. Due to steric hindrance, secondary alkyl halides also prefer to undergo elimination rather than substitution. For example, 2-bromopropene plus CH3CH2O negative and A positive at 330 Kelvin gives propene 79% and 2-ethoxypropane 21%. Reaction of alkyl halide with dry silver oxide. Ether can also be prepared by heating an alkyl halide with dry silver oxide. For example, ethyl bromide 2 moles plus Ag2O on heating gives diethyl ether plus 2 AgBr. From alcohols, ethers may be prepared from alcohols as well by dehydration of alcohols. Ethers may be prepared by dehydration of alcohol either in the presence of acid or heated alumina. Acid catalyzes dehydration. Symmetrical ethers can be prepared by dehydration of alcohols with concentrated H2SO4 at 413 Kelvin. ROH plus OHR concentrated H2SO4 at 413 Kelvin gives ROR plus H2O. CH3CH2OH concentrated H2SO4 gives CH3CH2O CH2CH3 plus H2O. Yield of ether, however, depends on the nature of alcohol, whether primary, secondary, or tertiary. Since in this reaction 2 molecules of an alcohol lose 1 molecule of water, therefore it is better called as intermolecular dehydration. Limitation: though this method is useful for large scale production of ether, it has two major drawbacks. The preparation of ether is always being accompanied by the formation of alkenes due to the intramolecular dehydration of alcohols. However, in case of primary alcohol, alkenes are formed only to small extent, which can be further suppressed by using a large excess of alcohol. In case of secondary alcohol, alkenes are formed in much larger amount than ether, but in case of tertiary alcohol, exclusive formation of ether occur. Thus, the order of dehydration of alcohol leading to the formation of ether follows the sequence primary, secondary, tertiary. Therefore, dehydration of alcohol is used only for preparing ethers from primary alcohol. This method is suitable for unsymmetrical ether because a complex mixture of ethers is always obtained. 3ROH plus 3 HOR dash concentrated H2 is our ROR plus ROR dash R dash O dash plus 3H2 mechanism. This reaction is an example of nucleophilic substitution reaction in which protonated alcohol molecule act as substrate and water as the leaving group and another molecule of alcohol as the nucleophile. The reaction may follow either first order kinetics or second order kinetics depending upon the nature of the alcohol used. In general, primary alcohol follow SN2 mechanism while secondary and tertiary alcohol follow SN1 mechanism. Catalytic dehydration. Dehydration of alcohols ether can also be achieved by passing the vapors of the alcohol over heated alumina at 523 Kelvin. For example, ethyl alcohol on heating 523 Kelvin IL2O3 gives dimethyl ether plus water by the action of diazomethane on alcohols or phenols. Methyl ethers can also be prepared in the excellent yield by the action of diazomethane CH2NH2 on alcohols, phenols in the presence of tetrafluoroboric acid HBF as catalyst. For example, tetrafluoroboric acid plus diazomethane gives ethyl alcohol ethyl methyl ether. From alkenes, ethers can be prepared from reactive alkenes by following two methods: direct addition of alcohols in the presence of acid as catalyst. For example, 2-methyl propene plus methanol gives 2-methoxy 2-methyl propane. The main disadvantage of this method is that sometimes initially the formed carbocation rearranges to the more stable carbocation, which then react with alcohol to form rearranged ethers. For example, 3,3-dimethyl 1-butane gives 2-ethoxy 2,3-dimethyl butane rearranged product and 2,3-ethoxy 2,2-dimethyl butane normal product. Indirect addition of alcohol. Alkoxymercuration reduction. Alkenes readily react with mercuric trifluoroacetate in the presence of an alcohol to give a alkoxymercurial compound, which upon reaction with NaBH4 in basic medium give ether in high yield. For example, propene plus mercuric trifluoroacetate gives 2-ethoxypropane. This two-step process is called alkoxymercuration reduction or alkoxymercuration demercuration and gives ethers in accordance with Markovnikov's addition of alcohol as alkene. The reaction does not involve carbocation intermediate, hence there are no rearrangement in this reaction. 3,3-dimethyl 1-butane plus ethanol plus 3-ethoxy 2,2-dimethyl butane. Absence of competing elimination reaction. From Grignard reagent, higher ethers can be prepared by treating alpha haloethers with suitable Grignard reagent. For example, methoxychloromethane plus CH3MgI dry ether gives ethyl methyl ether chloromagnesium iodide. Physical properties, physical state, color and odor. Dimethyl ether and ethyl methyl ethers are gases at ordinary temperature, while the other lower homologous of ethers are colorless liquid with characteristic ether smell. Dipolar nature. Because of the greater electronegativity of oxygen than carbon, the CO bonds are slightly polar and thus have a dipole bond and slightly polar and must have a dipole moment. Since the two CO bond in the ethers are inclined to each other at an angle of 110 degrees, the two dipoles do not cancel each other. As a result, ether have a dipole moment of 1.15 to 1.3 d. For example, dipole moment of dimethyl ether is 1.3 d and diethyl ether is 1.18 d. Boiling point. Ethers are isomeric with monohydric alcohols, but their boiling points are much lower than the isomeric alcohol. This is due to the reason that unlike alcohols, ether do not form hydrogen bonds. As the result, ether do not show molecular association, hence have low boiling points than the corresponding alcohols. Further, the weak polarity of CO bond does not affect the boiling points of ethers, which are about the same as those of alkenes with a comparable molecular mass. Solubility. Ethers containing up to 3 carbon atoms are soluble in water. The solubility of other lower ethers in water is comparable to those of corresponding alcohols. For example, like ethanol dimethyl ether is completely miscible with water. Similarly, both diethyl ether and N-butyl alcohol are soluble in water to some extent, 8 gram per 100 gram of water. The solubility of lower ether in water is due to the formation of hydrogen bonds between water and ether molecules as shown below. As the molecular mass increases, the solubility of ether in water decreases due to the corresponding increase in the hydrocarbon portion of the molecule. Ethers are, however, fairly soluble in common organic solvents such as alcohol, benzene, chloroform, acetone, etc. Density. All ethers have lighter than Water chemical properties. Ethers are relatively inert compound, almost as inert as alkanes. Under ordinary conditions, they are stable to base, dilute acid, catalytic hydrogenation, and to the most reducing agent. This is due to the reason that the functional group of ether does not contain any active site in the molecules as they compare to hydroxyl group of alcohol and phenols. Even though the oxygen atom in both these functional groups contain two lone pairs of the electron, however, under specific condition, ether undergo the following reaction. Reaction of ether and oxygen on account of the presence of two lone pair of electrons on the oxygen atom. Ether behaves as Lewis base and thus undergo reaction involving the formation of coordinate bond as discussed below. Action of concentrated acid. Formation of oxonium salt. The oxygen atom in the ether has two lone pairs of electrons. As a result, the ether behaves as Lewis base and thus dissolved in the cold concentrated inorganic acid to form stable oxonium salt. For example, ether gives dialkoxonium chloride, dimethyl ether, dimethyl oxonium chloride, diethyl ether, diethyl oxonium hydrogen sulfate. Formation of coordination complex. Being Lewis base, ether form coordination complex known as etherates, and Lewis acids such as BF3, LCl3, FeCl3, Grignard reagent, etc. Due to the formation of these complexes, Grignard reagent dissolved in ether. That is why Grignard reagents are usually prepared in ether. They, however, cannot be prepared in benzene because benzene has no lone pairs of electrons, hence cannot form complex with them. Reaction involving the cleavage of carbon-oxygen bond with halogen acid. Ethers are readily cleaved by the hydriodic acid or hydrobromic acid at 373 Kelvin form an alcohol and alkyl halide. For example, ether plus HX gives alcohol and alkyl halide. However, if excess of acid is used, the alcohol first formed reacts further with halogen acid to form the corresponding alkyl halide. The overall reaction may be then written as ROR plus 2HI gives 2RI plus H2O. Diethyl ether plus 2HI gives ethyl iodide plus H2O. Similarly, cyclic ethers are readily cleaved by HBr or HI to yield dihaloalkanes. For example, tetrahydrofuran THF plus 2HBr on 373 Kelvin gives 1,4-dibromobutane plus H2O. Reactivity of halogen acid. The order of reactivity of halogen acids are follows: HI, then HBr, then HCl. As discussed above, the cleavage of ether by halogen acids in fact involves a nucleophilic attack of the halide ion on the protonated either molecule, obviously greater the nucleophility of the halide and more the reactivity is the halogen. Since the nucleophility of ions are follow I negative, then Br negative, then Cl negative. Therefore, the reactivity of the halogen acids follows the same sequence HI, HBr, HCl mechanism. Ethers being Lewis base undergo protonation to form oxonium salts. Step 2. The protonated ether thus formed undergoes nucleophilic attack by the halide and either by SN1 or SN2 mechanism depending upon the nature of the groups R and R' and the reaction condition to form a molecule of an alkyl halide with the displacement of weakly basic alcohol molecule. If the group R and R' are primary, the reaction occurs by SN2 mechanism. If the secondary or tertiary, the reaction occurs by SN1 mechanism. Site of cleavage. The site of cleavage of unsymmetrical ether by halogen acid depend upon the nature of group R and R'. If both the group are primary, then alkyl halide is always obtained from the smaller alkyl group. Ethyl methyl ether gives methyl iodide and ethyl alcohol. If one group is methyl and another is primary or secondary alkyl group, the reaction occurs by SN2 mechanism. Due to steric hindrance, the halide and always attack the smaller alkyl group by CH3 group to give methyl added, while the bulkier alkyl group gives the alcohol. In one group is methyl and another is a alkyl group. The reaction occurs by SN1 mechanism and the formation of product is controlled by the stability of the carbocation resulting from the cleavage of the CO bond in a protonated ether. Since alkyl carbonate is much more stable than the methyl carbocation, therefore the alkyl halide is always derived from the alkyl group and the alcohol from the smaller group, methyl group. Example, tert-butyl methyl ether plus concentration HI SN1 reaction at 373 Kelvin temperature gives tert-butyl iodide and methyl alcohol. It may be emphasized that the high polarity of the solvent H2 present in the concentration HI 57% has favored SN1 mechanism. However, if the cleavage tert-butyl methyl ether is carried out with the anhydrous ether, the low polarity of the solvent ether would favor SN2 mechanism and hence I negative will be attack less hindered methyl group giving methyl iodide and tert-butyl alcohol. Tert-butyl methyl ether gives methyl iodide and tert-butyl alcohol. Cleavage of alkyl aryl and diaryl ether. In case of alkyl aryl ethers, the products are always phenol and an alkyl halide, never an allyl halide and an alcohol. Methyl alcohol plus iodobenzene gives anisole, then phenol plus methyl iodide. The carbon atoms of the phenyl groups are sp2 hybridized while that of the alkyl group are sp3 hybridized. Sp2 hybridized carbon being more electronegative repels the nucleophile, while sp2 hybridized carbon being less electronegative attract the nucleophile. In other words, nucleophilic attack by the halide ion occur more easily on an alkyl group, leading to the formation of an alkyl halide and phenol. Secondly, an phenyl group is much bigger in size than an alkyl group. Therefore, because of the steric hindrance of the bigger phenyl group, the halide ion attacks the alkyl group, leading to the formation of an alkyl halide and phenol. It may, however, be noted that the phenol is not converted to iodobenzene even with excess of HI. Diaryl ether are not cleaved by HI because both the carbon atoms to which the oxygen is attached are sp2 hybridized and hence repel nucleophilic halide ions. Ziesel method. The cleavage of alkyl aryl ether by hydrotic acid forms the basis of Ziesel method for the estimation of alkoxy groups such as methoxy and ethoxy groups in such ether. The non-weight of phenolic ether is treated with an excess of concentrated hydrochloric acid. The alkyl iodide produced as a result of cleavage of ethers by HI is treated with an ethanoic acid solution of silver nitrate. The precipitate of silver iodide thus formed is filtered, washed, dried and weighed. From the amount of AgI formed, the percentage of alkoxy groups can be estimated. With sulfuric acid, on heating with dilute sulfuric acid under pressure, ethers are hydrolyzed to alcohols. When heated with concentrated H2SO4, ethers react in the same manner as with the halogen acid to form an alcohol and an alkyl hydrogen sulfate. For example, dimethyl ether plus concentrated H2SO4 gives ethyl alcohol, ethyl hydrogen sulfate. Secondary and tertiary ethers, however, form alkenes. Reaction involving alkyl group, action of air and light, autooxidation, formation of peroxide. When exposed to air and light for a long time, ethers are oxidized to form hydroperoxides or simply peroxides. Diethyl ether plus O2 in the presence of light gives 1-ethoxyethyl hydroperoxide. It is a free radical reaction and oxidation occurs at the carbon atom next to the ethereal oxygen to form hydroperoxide. These peroxides are very dangerous compounds since they decompose violently at high temperature. Therefore, serious exposure may occur during the distillation of old samples of ethers if peroxides are not removed. Presence of peroxide is the old sample in ether may be detected by shaking them with freshly prepared solution of FeSO4 followed by the addition of KCNS. Appearance of a red color indicate the presence of peroxide. A simple method to remove peroxide is to shake an old sample of ether with either an aqueous solution of Ki or a ferrous salt. When ether peroxide are reduced to ether and I negative is oxidized to I2 or Fe2 positive. Salts are oxidized to Fe3 positive salt. Halogenation. Ethers react with Cl2 or Br2 to give substitution product. The extent of halogenation, however, depends upon the reaction condition. For example, diethyl ethers with chlorine in the dark to give alpha-alpha dichloro diethyl ether. However, in the presence of light and excess of chlorine, all the hydrogen atoms are substituted to give perchlorodiethyl ether. Epoxide. The three-membered cyclic ethers are called epoxide. In common system, these are called, but in the IUPAC system, they are called either alkene oxide, epoxy alkanes. For example, ethylene oxide. Synthesis of epoxide. There are two main laboratory methods for the synthesis of epoxide. These are epoxidation of alkenes. Alkene on treatment with peroxy acids are called peracids such as perbenzoic acid, M-chloro, perbenzoic, MCBPA, peroxytrifluorotic acid. In an inert solvent such as CH2, Cl2, CHCl3, CCl4 give epoxide oxidants. Due to the formation of epoxide, the oxidation of alkene with peracid is commonly known as epoxidation. Mechanism. Peroxy acid act like electrophiles of the reaction is believed to proceed by the following mechanism. From halohydrins, when halohydrins prepared by the addition of hypohalous acids to alkenes are treated with the base, HX is eliminated and an epoxide is formed. Mechanism. It may be noticed that the synthesis of epoxide by base treatment of halohydrins is actually an intramolecular Williamson synthesis. Bromohydrin. Manufacture of ethylene oxide. It is manufactured by passing a mixture of ethylene and air under pressure over silver catalyst. Ethylene Ag ethylene oxide. Chemical reactions of epoxide. Acyclic ethers and cyclic ethers containing 5 and 6 membered rings such as tetrahydrofuran and the 1,4-dioxane are quite inert and are often used as solvent. 3 membered cyclic rings are epoxide on the other hand are highly reactive, and this is due to the reason that 3 membered rings are highly strained. They have considerable angle strain. Because of their highly strained nature, epoxide ring can be opened by the variety of nucleophilic reagents such as Mulder condition. Consequently, most of the reaction epoxides are the ring opening structure. These can be catalyzed both by acid and base. Acid catalyzed ring cleavage of epoxide. Due to large angle strain, epoxides are readily hydrolyzed by dilute mineral acid at room temperature to form corresponding 1,2-diols glycols. For example, ethylene epoxide plus H2O gives ethylene glycol. Similarly, halogen acids in alcohols in the presence of acid can bring about the cleavage of epoxide mechanism. In the acid catalyzed hydrolysis of epoxide, the oxygen atom of the ring first accepts a proton to form protonated epoxide. The protonated epoxide then undergoes nucleophilic attack by water to give trans 1,2-diol. Base catalyzed ring cleavage of epoxide. Unlike ordinary ethers, epoxide can also be cleaved under basic conditions. Similarly, sodium alkoxide ammonia amines can bring out cleavage of the epoxide ring. Due to the greater electronegativity of oxygen than carbon, the carbon atom of epoxide ring carries a small positive charge and hence can be easily attacked by the strong nucleophiles such as hydroxide, alkoxide, peroxide, ammonia. Stereochemistry of ring cleavage of epoxide. Both acid and base catalyzed ring opening reaction of epoxide occur by SN2 mechanism. Therefore, attack of the nucleophile always occurs from the back side of the leading to the formation of trans 1,2-diol. Reaction with the Grignard reagent, organolethium reagent. Epoxide also undergo ring opening reaction with the Grignard reagent and organolithium compound. The addition products initially formed upon hydrolysis give primary alcohols containing 2 carbon atoms more than Grignard or the organolithium compound. The epoxide generally used in this reaction is ethylene oxide. Regioselectivity orientation of cleavage of epoxide. The unsymmetrical epoxide can undergo ring opening in two different directions and hence can give different products under acidic and basic condition. In acidic medium, the nucleophile generally attacks the more substituted carbon, while in the basic medium, the nucleophile attacks the less substituted carbon. For example, 2,2-dimethyloxyrane gives 2-methoxy, 2-methyl, 1-propanol. 2,2-methyloxyrane plus CH3O negative CH3OH gives 3-methoxy, 2-methyl, 2-propanol. Although both the reactions occur by the same SN2 mechanism, the difference lies in the stability of the transition state. In the acid catalyst cleavage of epoxide due to the protonation of epoxide, since epoxide carbon atom carries a small positive charge, the magnitude of which depends upon the substitution. Since more the highly substituted carbon can accommodate the positive charge better, therefore the more highly substituted carbon has a fair amount of carbocation character and hence gets attacked by the nucleophile. Thus, in contrast, in the base catalyst reaction, there is no protonation and hence none of the epoxide carbons has a fair amount of carbocation character. Thus, therefore, like SN2 reaction, the attack of nucleophile is controlled by steric factors. Evidently, the nucleophilic attack will occur preferentially at less hindered carbon atom. Thank you.